Dalton law of partial pressures. The Dalton law of partial pressures indicate that pressure depending on the total number of gaseous particles, not on the type of particles. The total pressure exerted by a gas in a mixer in the sum of the partial pressure of the those gases. Examples of Dalton law of partial pressures: the total PHE plus PR 2 atom plus 4 atom, total is 6 atoms indicated in these images. This is helium, the PAR, total 2 plus 6, total containing gases 6 atoms. The Maxwell relations of temperatures and volumes, pressures and entropies. Deriving the Maxwell relations. First, start with the noun equation states such as that of internal energy du equal to TdS minus PdV. The next, take the total derivative of with respect to the natural variables. For examples, the natural of internal energy are entropy and volumes. Du equal to dou U by dou S power of V, or ds equal to dou U by dou V equal to dV. The deriving the Maxwell relations continuations. So now that we have a total derivative with the respective to its natural variables, we can refer back to the original equations of state and define in the examples T and P. So du equal to TdS and PdV, PV, the process lines and temperatures lines highlighted by the different colors in these images. We must now take into account of rule of partial derivatives. Dou square f divided by dou x dou y equal to dou square f by dou y dou x. When taking the partial derivative, again we can set both sides equal, and thus we have derived the Maxwell equation relations. Dou d divided by dou v s into s equal to minus dou b divided by dou s into v. The using of a Maxwell relations can be derived from the basic equations of state, and by using the Maxwell relations, working equations can be derived and used when dealing with experimental data. The basic equations, Maxwell relations, working equations. In these images we can see the equations, Maxwell relations and basic equations. The Clausius-Clapeyron equations, the basics idea. That provide the mathematical relationship equations that describe any equilibrium state of water, the function of temperatures and pressures, account of phase changes at each equilibrium state, each temperatures. This is a liquid area, sublimations, the vapor 0, 100, 374 degrees Celsius. The sections of pressure volume and pressure temperatures, the diagram for which Clausius-Clapeyron equation is derived the following slides. This area highlighted by different colors. This area containing the fully liquid. This is a critical point. The above this line, the crossing the left side of column, fully contained by the vapor, is the temperature lines. In between in the mid of this area highlighted by this area converted as a partially liquid and vapor containing these areas. Fully liquid converted to vapor by heating, partially mixed with the liquid and vapor, fully converted to the vapor in these slides. The mathematical derivations of Clausius-Clapeyron equations. Assumptions: our systems consist of a liquid water in equilibrium with the water vapor at saturation conditions. We will return to the Carnot cycles. mentioned the isothermal process in red color, adiabatics in blue colors. We can see these variations. The horizontal lines mention the volume, vertical lines saturated vapor process. Isothermal process to isothermal, mention the isothermal process in the red color line, blue color is adiabatic. A, B, C, D. The temperatures T1 to T2. Next one is the temperatures lines mentioned A, D, B, C.